Hello everyone, welcome back to part 2 of lecture 9. So, we were discussing about the image classification in part 1 and we will continue that discussion here. So, when we talk about the classification, the image classifiers can be trained using two ways. One is learning techniques, another one is feature set, right. So, what is learning technique? It enables to learn the changes in a system that improves the performance of the same task in the next iteration, right. So, like driving, cooking and solving mathematical formulas. So, you might notice this, that when you drive, initially you might have some problem. Slowly, every time you learn with your mistakes and you improve yourself, and slowly you become the good driver. Now, similarly for the cooking, the more you cook, you will have more experience and you will be making more tasty foods, right. And this one is more relevant when you try to solve numericals. Slowly you improve your skills and slowly you will be skipping in between steps because you do it in your mind, you do not have to write them. So, your speed will be very fast in solving a mathematical formula, right. The same way image classifiers learns in every iteration and then they train themselves and your accuracy will be improved. So, there are two major types of learning. So, as we discussed, supervised and unsupervised. Supervised learning, it requires the information at the beginning of the process by the analyst and it will be completely controlled by the analyst or the user, right. Unsupervised, it learns through some standard scientific laws and recognize unknown patterns using the data statistics, right. And the other one is the feature set. Based on the attribute of the input data, the pixels are assigned to different classes. So, when you are having very high number of points information or the ground control points from the field, you can directly map them as vegetation, water body or maybe some other class. The supervised image classification. So, classifier is supervised or guided by the analyst with his expertise or knowledge. The required number of classes is identified by the analyst, whether you want 5 classes, 10 classes or 15 classes in your image, that has to be decided by the analyst. When we talk about unsupervised image classification, classifiers group the image pixel into different classes, identifying them using statistical similarity. If the statistics is same, if the mean, median, mode, that you will see, and there are many other ways that you can do the clustering and then pixels will be assigned to class 1, class 2 or class 3. And there is one more which is hybrid image classification. So, here basically you will go with the unsupervised classification. So, you start the process with unsupervised classification and then subsequently you follow the supervised classification. So, then this will be known as hybrid image classification. Now, let us understand about the training data, because when we talk about the supervised classification, we have to have the training data, otherwise it will become unsupervised. So, what are the different parameter or cautions that we have to follow? So, we will see some of the details about the training data. The training data should represent all the desired classes. So, if I want 5 classes, so corresponding to those 5 classes, all the data sets should be captured in the field. It should address the spectral variability, means within a class, if you have different objects, let us say vegetation, if you are changing the vegetation species or your area is having 5 different vegetation species, so you should have the location of those 5 different vegetation species, so that the variation in the DN values or the reflectance, that should fall under one class, which is vegetation. It is based on the field or image information, because training data is completely the location value and the class information. Samples of training data should be geographically well distributed. So, it should not be clustered into one part of the image, right. For a bigger class, the training data should be large. So, if this much area belongs to forest, so you have to represent all these pixels. It should be well distributed and more number of points should be there for the forest. To improve the accuracy of the classification, training data can be modified. Suppose if you have used this set of pixel for the classification training and result is not very good, then you can go back and then modify your training data and then see the result. So, when we talk about the classification techniques, the supervised and unsupervised classifiers. So, here you can see in unsupervised classification, there are two methods which is globally used. First one is k-mean and another one is isodata. In supervised classification, minimum distance to mean, parallel pipe, maximum likelihood, support vector machine, artificial neural network, binary encoding, spectral information divergence, non-parametric classifiers. This list is very long, right. So, here you can use one of them to see how your data is providing you the input, and then maybe if the results are not satisfactory, you can try some other method, modify your training data and then you can see the result. In general, the spectral classifiers are used to classify the hyperspectral data. So, when we talk about the high dimensionality data, so for example, hyperspectral data, so those are the data which has different information, they are having high spectral resolution. So, the multispectral classifier, the names that I mentioned in the previous slide, some of them are completely dedicated to multispectral. Some of them can be used with the high dimensionality data. So, here in general, spectral classifiers are used to classify the hyperspectral data. So, spectral angle mapper, mixed tune matching filtering, spectral feature fitting, support vector machine, binary encoding and random forest. These are popular in classifying the hyperspectral data. So, any one of them or maybe a combination of them can be used to classify the hyperspectral data, right. So, let us talk about this SAM, spectral angle mapper. So, here for large dimension data, estimation of band statistics and distance for each pixel is a tedious process, because when you understand the multispectral classifier, you will understand how tedious it is to find the band statistics and distance from each pixel to the class mean or category, right. So, spectral angle mapper technique is very efficient in handling such large dimension data. So, large dimension means more number of bands. SAM is a spectral classifier that determines the spectral similarity based on angle between the pixel and reference spectra. So, what we will do? We will try to plot this 2 into this n dimension, right. So, suppose this is target, this is your reference, because here we are talking about the high spectral resolution. So, we are using the spectral information to classify our data. It can be from library or it can be from field or from lab, right. So, this SAM treats both pixel and reference spectra as a vector in a space where dimensionality is equal to the number of bands. Remember I mentioned ND plot, that means the ND is equal to the number of bands. Reference spectra used in SAM can be acquired in the laboratory and field or can be extracted directly from the image. The end members that we discussed in the hyperspectral, so those end members can be extracted from the image itself. In an n-dimensional feature space, pixel and reference spectra should have both magnitude and an angle. So, here we will have the magnitude and the angle, right, at what angle they are different from each other. A small angle between the pixel and reference spectra indicates high similarity. If it is close to each other with respect to this theta, then they are more similar in nature. If they are far, then they are not. High angle indicate low similarity. So, this high angle and this is low angle, right. Here this particular plot is meant to explain this SAM. Here this R is the reference spectra, it is from let us say from library or from lab measurement or from field measurement, right, that we wanted to use as our training data for this SAM classifier, right. Now, when we are using this, we try to find this theta. So, this theta is calculated using this particular equation, and here the Ti is the target spectrum, Ri is the reference spectrum from the library, field or lab, I is the number of input spectral bands, it can be 200, 300 depending upon which data you are using, and theta is the angle between the target and the reference spectrum. So, if it is more, they are not in same class. If they are very close, then they are in the same class, right. So, a threshold value is used to specify the maximum acceptable angle for the separation between the pixel and reference spectra. So, I can put a threshold of 1 degree or 2 degree or 3 degree. So, depending upon that, the system or the method will decide whether they belong to same class or they belong to different class, right. So, similarly using this SAM, this image has been classified, and this you can see here basalt, anorthosite, norite, then pyroxenite, olivine, basalt, Fe basalt, those are mapped in this particular image, right. So, this is a very good method. So, I thought of covering at least one method for the hyperspectral, because in the application part we will be referring this SAM, right. Now, as we discussed, the ultimate aim of remote sensing image is to provide the input for your analysis, right. And once you generate the input, you should be very confident, or you should have a value that this input is 60% correct or 70% correct or 90% correct, right. So, after doing the image classification, accuracy assessment is mandatory. There is no way out. So, you have to estimate the accuracy of your output result. The ultimate aim of a remotely sensed image is to produce the thematic map or to be a part of decision support system. Without an accuracy assessment, the result of classification is of 0 value. To support the result of a remotely sensed image, overall and class wise accuracy needs to be estimated. So, here we will have class wise or overall. Class wise means if my image is having 4 class, let us say this. So, this is forest, water, urban and maybe vegetation or maybe some other class, right, bare land. So, whether my whole classification, the overall accuracy is 60%, but class wise my accuracy can be less or more. So, some of the classes may be 90% accurate, some of the classes may be 60% accurate, some of the classes can be 50% accurate, and on an average you are getting the overall accuracy of 70% maybe, right. So, we need to have this data statistics about the image classification, and on that basis only we will be telling that this particular image which we have produced by the classification technique is 60, 70 or 80% correct. In general, accuracy can be estimated using ground truth. So, the ground truth is the pixel whose location values are known. So, we go to the field, we collect the latitude, longitude and then the class information, and that we identify on the image, the classified image, and then we see whether the classes which are classified is correct or not, right. So, these set of pixels are known as the test pixel, right. So, this is one example. Here you can see the satellite image is on the left side and right side is the classified image, and this is the table. So, this legend can be used to refer whether this color is urban or mining area or rural area or cropland or agriculture land or fallow land. So, this color code is helping us to understand how much area is covered with a particular class or category, right. So, after accuracy we will be telling that this particular map is 60% correct or 90% correct, right. So, once the ground truth, the test pixel has been decided, the classification has been completed, a tabular data which is known as confusion matrix, right, is generated to estimate the accuracy. A confusion matrix is also called as error matrix. This table is used to estimate the class wise and overall accuracy of the classification. So, class wise means whether it is for forest, how much accurate it is, for water body, how much accurate it is, or overall accuracy, the whole classification method is 60, 70 or 80% correct. Row of the confusion matrix are reserved for the information derived from the classified map, whereas the column are reserved for the ground truth. That is, from the ground you are collecting the test pixels, right. So, those are fixed in the columns. We will see that confusion matrix here. So, here the row is here map classified and the column is here ground truth, right. Now, you see we have classified our image into 5 classes. So, this is class 1, class 2, class 3, class 4 and class 5, and this is the total number of pixel, and here you have user accuracy, here you have producer accuracy. So, similarly the classified map is also having the 5 classes. So, class 1 versus class 1, right. So, that says that 7 pixels are correctly classified as class 1 with respect to ground information, right. 8 pixel are correctly classified as class 2 with respect to ground truth. 25 pixels are correctly classified as class 3, and here 12 pixel are correctly classified as class 4 and 8 pixel is correctly classified as class 5. So, this kind of table you have to generate for your image, right, and once you add them, this is the total number of pixel which are correctly classified, 74, and when you add this particular row, so now we will see the row. So, this is image classification, right. So, this particular side is fixed for image information. So, if you see this row, 7 plus 1 plus 4 plus 1 plus 1 is equal to 14. So, 14 pixels were classified as class 1 with my classifier, right. But according to ground information only 7 are correctly classified, rest 7 are belonging to some other classes. So, we can say 50% is correctly classified, 50% is wrongly classified. Similarly, for class 2 if I see 8 is correctly classified, so this is coming 8, right. For class 3 25 are correctly classified and these are wrongly classified. For 4 it is 12 1 1 and here it is 8 1 1. Here when you see the row, you have to see how many pixels are correctly classified, how many are wrongly classified. Now we will go with the column. So when we look at this column, so here the first column, right. So the first column says that 7 of the ground truth are matching with class 1 and one of them is falling into class 3. So the classifier has wrongly classified this 1 into class 3 and 7 is correctly classified, right. So similarly you have to go with all the columns and then you have to analyze your result. But to say a number you need to calculate, right. So what we will do? We will go with the producer accuracy. Number in diagonal cell of the error matrix and total number of the pixel in column, right. So this is the value 7 by 8, right. So this particular class, class 1 is having 87.5% producer accuracy. That means if I am the classifier, I am the user, I will say that I have produced 87.5% accurate result for class 1, right. If I have generated this particular image or if I have generated the classified map, then I will become the producer, right. So as a producer, I have produced 87.5% accurate result for class 1. But if you are the user of my results, then you will be calling it in this way. So user's accuracy will be this correctly classified and then total number of the pixel covered in that, right. So here the accuracy will become less. So if you compare with the producer accuracy, user accuracy is less. So as a producer, I am saying I have produced more accurate result, but as a user you will say no, you have produced less accurate result, right. So then comes the overall accuracy. So this is sum of all these diagonal pixel and total number of the pixel that is used in this particular accuracy assessment, right. So that will be your overall accuracy. Now let us talk about the Kappa coefficient. This is another way of providing the accuracy value. So when we talk about the Kappa coefficient, it estimates the accuracy of a classified image which measures the proportional, that means the percentage improvement by the classifier over a randomly assigned ground truth, that is your test pixel, to different classes, right. So here what we will do? We will try to calculate the Kappa coefficient. So the Kappa coefficient, this k, small k, is equal to n into a minus b divided by n square minus b, right. So here n is the total number of pixels used in the accuracy assessment, that is 74. Total number of correctly classified pixels, that is 60, and the b is multiplication of row and column values corresponding to class or category, right. So 8 multiplied with 14 plus 9 multiplied with 8 plus 31 multiplied with 28 plus 15 multiplied with 14 plus 11 multiplied with 10. That will give you the b, right. Now, you use these values here and then you calculate the kappa coefficient, right. So, with this I will end this lecture and we will continue this course with lecture 10 and we will start the next module in the next lecture. Thank you very much.